So I'm like, oh, I got something I can actually improve on. This is exciting. Okay, so we were working on this problem the other day. Uh, what we did was so let's kind of review where we were. So pull out your sheet because you didn't hand them in. So what we started with was this more complex uh, arrangement of 6 capacitors. And so we hook up a battery just like we did the other day, and almost instantaneously the capacitors would become charged. And there's going to be a voltage across the capacitors, there's going to be a charge on the capacitors. And the way you can solve this is by collapsing these 6 capacitors down to a single capacitor, and then, which is what we did. So we came up with what's called an equivalent capacitance. And the rules we use, if capacitors are in parallel, which is like this, you just add the capacitance values together. And that's because the voltage across each capacitor is the same. So the voltage is what drives how much charge you can put on a capacitor. So we collapsed those 3 parallel capacitors into one by adding them together, and then we took these 2 capacitors and added those together to get the equivalent capacitance. And then once we've reduced it down to 3 capacitors, we use the equations for capacitors in series, and in that case each one of them has the same charge. So when they're in parallel, they have the same voltage. When they're in series, they have the same charge, and that's because the only way to charge the capacitors in the middle is to steal some electrons from the other capacitors, because there's no current flows across those 2 plates because it's just air. Okay, so we combined those 3 capacitors into a single capacitor, and we got a number which was 15/19, and the units are farads. So what we're going to do now is we're going to go take that information and go back to figure out what the charge and the voltages are on each capacitor that we started with. So we basically just use the definition of capacitance, which capacitance is equal to charge divided by voltage. So if I multiply, they're not coming in, are they? Good, okay. Now I'm paranoid because I've been doing it for like 2 years on Fridays. Nobody ever came in. So last Friday, I guess did I tell you that they wanted to use this room, and so they had to use another room, which turned out to be a better room, but somebody had reserved this room and they came to use it and we were in it. So that I got this email later that day from my boss saying, it's fine if you use the room, but please just reserve it. So I was going to do that all week, and then I forgot. So I sent an email this morning. Can I please reserve the room? Let me know if it's okay. But the secretary who works there is, she works part-time, so she may not be in. So I'm hoping that I don't get in trouble again. Okay, so back to here. So what we're going to do, in the case of when we have the single capacitance, we've got the voltage across the capacitor, which is 9 volts, and we have the capacitance. So I should be able to figure out what the charge is on this single equivalent capacitance. So we'll do that. So the capacitance was 5/19 times the voltage, which is 9 volts. And we could do this all as decimals, but we're just going to do fractions just to have practice with fractions. So 135 divided by 19. And the units are coulombs for charge. Okay, so that's the charge up here. So I can go back here and say, well, I can say the charge on this one capacitor, Q, is equal to 135 divided by 19 coulombs. Okay, and you look on your sheet, you'll notice that, well, actually we go this way, so let's do that. So this charge of 135 over 19, that's what's going to be, well, it's, yeah, let me steal something here. So the equivalent capacitance here was 10 and 6. So let me write that down. So 10 microfarads, 6 microfarads. Now, as far as what do we do with this charge? Well, what happens is this charge, which is on a single capacitor previously here, gets on each one of the 3 capacitors. So what we can say is, Q sub A is equal to 135 over 19 coulombs. Q sub B is equal to 135 over 19 coulombs. And Q sub C is equal to 135 over 19 coulombs. And that's because, as I said, you can't, basically what we're doing here is what we see at the terminals of the equivalent capacitor are the same things that we would see at the previous step. So if we go back to this the previous drawing, and we thought, okay, how do I talk about charges? Well, on this plate, there's a charge of positive 135 over 19 coulombs, and on this plate, there's a charge of negative 135 over 19 coulombs. So if I go over here to this here, now this outside plate still has to have the same charge. It has to have 135 over 19, and this one has to have 135 over 19, and for everything to balance out, this has to be 135 over 19, this has to be 135, and they all have to be the same. So now what we do is we use the same equation, but we solve for voltage instead of for charge, because now I know the capacitance and I know the charge. Over here we knew the capacitance and the voltage. So now that I have the charge and the capacitance, I can calculate the voltage after I've solved for it. So let me do that. Let me add a page here so we can see what we're doing. So the voltage across this 10 microfarad capacitor is going to be equal to 135 divided by 19 coulombs divided by the divided by the capacitance, which is 10 microfarads. And we're just going to leave the micro in there because this is actually, sorry, let's go back. These are really microcoulombs. Let me fix that. I said we didn't have to deal with the micro, but so let's go back. And so when we did this, we ended up with that, but it really was, the equivalent capacitance was 15/19 microcoulombs. It's just I didn't want to have to put microcoulombs on in there. So this is microcoulombs, and this, I mean, yeah. So this is actually, I got it wrong. Make sure, microfarads. Sorry, go back here. Sorry, I messed it up again. Capacitance is farads, not coulombs. So that's microfarads, that's microfarads, this is microcoulombs. Okay, I think we're okay. Let me go back one step, make sure I'm using, yeah, farads, farads, farads. Okay, so the chargers are all farads. The chargers are all coulombs. Now I've got the micro in there, I'm happy. These are micro, these are micro. Okay. Okay, so now we can do it. The micro stuff cancels out. That's basically what happens here. So if I do the fraction, I'll have 135 divided by 19 times 10, and the units are volts. So this one you can divide by 5. You can't divide by 10. So let's divide that by 5. So 135 divided by 5 is 27. And in the denominator, I'm going to have 19 times 2. 19 times 2, 38. So it's that many volts. Okay. So that's the voltage across capacitor A, or this equivalent capacitor A. Then you can do the same thing for we're going to call this, what does that stand for? It looks like a 4, so I'll use it. Voltage 4, you take the charge, which is still 135 over 19 microcoulombs, and you divide by 1 microfarad, so you get 135 over 19 volts. And then V sub B, which is the equivalent capacitance there, you take 135 microcoulombs over 19 divided by 6 microfarads. So can you divide 135 by 6? Yes. 135 divided by 6 is, no, you can't. Okay. So you can divide it by 3. 135 divided by 3, hopefully. 45. So this is 45. So if you divide this by 3, you've still got 2 left over. So that's 45 over 38 volts. And if I did all this right, those 3 things, if I take VA plus VB plus V4, which is 27 over 38 volts, plus B is 45 over 38 volts. And this is, if I want to go to the same denominator, so it'll be 270 over 38 volts. If I add that, so 27 plus 45 plus 270 is 342 divided by 38, and 342 divided by 38 is 9. Okay, you didn't think that was going to happen, did you? Because you get these crazy fractions and you're like, no way, it's not going to work out. But it is, okay? So you can always check yourself by doing those kinds of checks, because you know what, I've got 3 capacitors and it's fed by a 9-volt battery, so the total voltage drop has to be 9 volts for everything to balance out. Okay, so we can write those numbers in, I guess, on our picture now. So let's do that. So the voltage across capacitor A is 27 over 38. Across 4 is 135 over 19 volts, and the voltage across this capacitor is 45 over 38. Now, one more step. So we're going to take those numbers, and we're going to go to the next picture right here. So what I have is the voltages. Voltage A is 27 over 38. So I'm going to write that in there. There's no space. You just have to draw it out in space there. So you get 27 over 38 volts. This voltage B is 135 over 19. Probably should just leave it as 38s, but let's just 135 over 19 volts. And the voltage across these 2 capacitors is 45 over 38 volts. So now, what do we have? Well, we have voltage and we have capacitance. So we can figure out the charge on each one of those 3 capacitors. The same here, we have the voltage and we have the capacitance, so we can figure out the charge. Here we have the voltage, and here we have the capacitance. So we solve, in this case, for charge again. So let's add a page here so you can see this. So basically what I'd have is Q1, the charge on capacitor 1, is going to be equal to, let me see, what is this? Capacitance is charge divided by voltage, so charge equals capacitance times voltage. So what we're going to do is we're going to have 2 microfarads, which would be C1, times V1, which is the same as VA, which is 27 over 38 volts. So multiply that out. Well, that's easy. It's 54 over 38 microcoulombs. So that's the charge on capacitor 1. Charge on capacitor 2 is going to be 3 microfarads times the voltage, which is 27 over 38 volts. So 27 times 3 is 81. So you get 81 over 38 microcoulombs. And Q3 is going to be 5. So we take 5 microfarads times 27 over 38 volts. And 5 times 27 is 135. So you get 135 over 38 microcoulombs. Okay. Now, if I add Q1 plus Q2 plus Q3, it should be the same as the charge that I had here, 135 over 19. Okay. So what I'm doing is I had this much charge on my single capacitor. That same amount of charge has to be distributed amongst these 3 capacitors. So let's see what happens. So you get 54 plus 81 plus 135 all divided by 38. 54 plus 81 plus 135 is 270 over 38, and the units are microcoulombs, and that's 135 over 19 microcoulombs, which is what I got here, 135 over 19 microcoulombs. So I'm going to ask you to do the other bit here. So figure out what the charge or the charge on this capacitor is using this voltage and this capacitance, and then find out what the charge is on either one of these using this voltage and those two. And they should all end up being, if you add, well, this one should be 135 over 19, which obviously it is because you've got 1 microfarad. And the sum of these two should also be 135 over 19. So I'll give you a few seconds or minutes so that you can do the calculations instead of me doing it. So yesterday I went over my fall student evaluations with my boss. He got a good laugh out of the neo-Nazi leftist comment. I didn't get any trouble for that. He thought it was funny. So I didn't think I would. So next time, try something even worse. It's not just kidding. So yeah, you get 135 over 19 microcoulombs for Q4. You get 90 over 38, which I could simplify, but I'm going to leave it there. 90 over 38 microcoulombs for Q5, and 180 over 35 microcoulombs for Q6. And if you add this plus that, you get 270, which is the same answer. 270 over 19, over 38 is the same as 135 over 19. So anyway, that's it. Am I going to make you do that during a test? This part, yes. This part, no. Okay. So you'll need to be able to figure out the equivalent capacitances of a circuit of some sort or another. Pardon me?
How do you know that it's 135 over 19?
Which one?
We're working on
The last one?
6, yeah.
Why do I know it's that? Because why did that? I know that they add up to be that. Because if I go back to my original single capacitance, which I got to be 15 over 19 microfarads, and I use 9 volts, I get this charge of 135 over 19. So that's what I know has to be on the outside of these. And so that charge, that information has to kind of pass back through the whole thing. So the sum of these three have to be 135 over 19. These have to be 135 over 19. This one has to be 135. It's just, yeah. So that's it for chapter 16. We're going to go to chapter 17 now. So what do we do in chapter 16? We talked about electric potential energy. So that's the amount of work that's required to move two charges closer or further apart relative to each other. And if you have two positive charges where they're repelled, as you push them closer together, they're going to have positive potential energy, increase the potential energy. If you have two that attract each other, a positive and a negative, then as you get closer together, the potential energy actually gets less. And then we talked about potential energy per unit charge, which is electric potential, and that's voltage. So that's what it's and the whole thing was dealing with, instead of dealing with vectors, we were dealing with scalars. And because we introduced voltage, then we talked about capacitance. And capacitors charge almost instantaneously, because what happens is you put a battery onto a capacitor, you create this electric field, which then pushes the electrons to one plate and takes them from the other, and you create this little sandwich where there's positive charges on one plate and negative charges on the other plate, and they're attracted to each other, and also they generate an electric field inside that space between the two plates. Just realized I hadn't talked about dielectrics. We'll come back to that. So anyway, that's capacitors. So now we're going to talk about the other big thing, which is current. So the current, what is the current when you charge that capacitor? Well, it's pretty high, but it doesn't take. It's such a short period of time that it doesn't cause the wire to burn up. That's if you have current, a high amount of current for a long period of time, then you can have things get overheated and burn up. But most things don't have an infinite current. They have a lower current for various reasons, and usually it's because of the resistance of the material to the flow of electrons. So what we basically have, I don't know what this looks like, a little person. I'm not sure what that little person's doing there, but what I have is I have a conductor or a resistor, it doesn't really matter, and these electrons are going to move. What you're going to do is you're going to impose an electric field through a battery to the different sides of this wire. So here's, there's an electric field that goes, which way the heck does it go? It goes this way. And so the actually has, for the electrons to be moving this way, it actually has to go the other direction. So let me drag this back. So you'd have an electric field going this way, but the electrons would move through this pipe of conductive material. So they'd go like this. Okay. So the question is, how fast do they move? Do they go like really slowly, or do they go whoo? Okay. So that's what current is measuring. It's how much charge moves through a given area per unit time. And so it's looking at the definition, charge per unit time, charge is coulombs and time is seconds. So current is coulombs per second, but we give that a special name too. We call it an ampere. So 1 coulomb per second is 1 ampere, or we use amps for short. And we use capital A to even though these are lowercase, we use capital A for amps, for amperes. And 1 amp is not that huge a current. When we talked about 1 coulomb, that was a lot of current. That was a lot of charge. 1 farad is a really big capacitor, but 1 amp is not that huge. For example, in your household circuits, you have things to limit the current called circuit breakers, and they may be 20 amps or 30 amps. So a hair dryer might be pulling a couple of amps. The Arduino, if when we do the Arduino stuff, those actually are close to milliamps. So those are the. Let me just add a page here. Now, from a calculus standpoint, what we say is the charge, the current. The current, which we use a small I, here we use a big I, so that's current. Okay, so I is current. Small I for current that varies with time is equal to the derivative of the charge with respect to time. So it's the rate of change of charge with respect to time. Here it's the amount of charge moving through a certain space in time. So it's basically the same thing. That's the calculus definition. It's still coulombs per second. Now, the thing that the new electrical element that comes into play when you're talking about current is a resistor. So, so we'll talk about resistors in just a second. But that's to remind me. So you can actually do this calculation of what the average movement of electrons in terms of meters per second it is when you have a reasonable amount of current. And you think, if I disconnected my computer and I stuck some wires in here and went like that, I would get shocked, right? Okay. And it would be painful and it would be immediate, okay? So you would think that the electrons are going to move from the plug to my tongue. I don't know why I chose my tongue. It doesn't really have to be my tongue. I'm thinking of a battery. You stick a battery on you. How many people have done that? Take a 9-volt battery and stuck their tongue on it. Yeah, all the guys. So you think that this thing's moving really fast, right? that the electrons must be moving at a super high speed. And I'm not going to go through the total derivation, but what you can do is you assume that each molecule of the conductive material, which say is aluminum or something like that, has a free electron, and so you can calculate the number of electrons that are available to move through the cable by taking the material, assuming each one you have a free electron in the structure, and using Avogadro's number and also some math like that. And what it turns out is that the actual bulk velocity, which means the average movement of all the electrons along that wire, is really slow. It's like 0.00 something meters per second, which is that's even slow for a snail. Okay, it's much smaller than you think. So why is it that when I stick my tongue on the when I get electrocuted, why does it seem to happen? You think if it's moving that slowly that I could just sit there and say, okay, I'm waiting for the electrons to get through there. What's going on. So, but it doesn't happen that way. And the reason is because, let me just demonstrate it. So let me make up some little electrons here. So those are my electrons. I'm going to put those all together. Whoops, didn't mean to do that. We're going to collect all those electrons, attach them together, and where are we at? Format, group. Okay. So now I'm going to put my wire around this thing. So what happens is when you apply the electric field, the electrons move. Okay, they move as a group. Why did it do that? I thought they were all grouped together. Let me do it again. They're supposed to be all attached. Format, group. Okay. So what happens is the electrons move as a group like that. Not in unison. They're bouncing around like this because of thermal energy. But the electric field is going to cause them to move in one direction. So assume this is the side that's attached to the wall, and the other. Did that again. The other side is. So what I'm doing is I'm getting shocked by the electrons that are just sitting there waiting for me. So there's the electrons here, and the electric field pushes enough of the electrons that are right at the tip of this, where the conductor is, into my tongue to electrocute me. It's not the electrons over there. It's not like it goes room like that. It's kind of like if you were blowing in a big long tube which was filled with water, and you push it, you apply pressure to that tube. The water that's near your mouth is not the water that's going out the other end. It's the water that's already there. Okay, so if you want to look at that, you can, but I'm not going to go into the details. Okay, so now we're going to talk about resistors. So resistors are something that are they conduct electricity, but they don't conduct it anywhere close to something like copper or silver or aluminum. But they're not completely an insulator either. So they allow some flow of electricity, but a limited amount. So you've got wires that are connecting things in an electric circuit. Those are conductors. Then you have the resistive elements. And what they're doing is they're basically limiting how much current can flow through your wire. If you didn't have resistors, and that's why we tell you not to hook up the LEDs without a resistor, you'd get a very high current. And as long as you could keep providing the electrons to keep that current going, you could cause people to be dead or to burn stuff up, whatever it is. Okay. So as we saw the other day, the schematic representation of a resistor is just this kind of squiggly line. It's kind of like a jigsaw, like a saw thing. It's not like a sine wave. So we make it so notice these are little abrupt changes in direction. And what you do is you apply a voltage across the resistor just like we applied the voltage across the capacitor. When you apply the voltage across the capacitor, you create an electric field. We also have an electric field across the resistor, but we're not storing energy. We're dissipating energy. As these electrons try to move through this material, they're bouncing off, and their movement is impeded, and that takes energy to make things move through something. Like if you have a hose with a valve, the valve is you're going to adjust the flow of the water by turning down the valve, and so a resistor is kind of like that. Now, if you were to plot, so let me add a page here. If you were to plot current as a function of voltage for a resistor, what you would find out is you would get a curve that looks like this. So this one is, let me just see, voltage, resistance, I have to write it down. Resistance equals voltage divided by current. So this is voltage and this is current. And the slope of this line is the resistance. And it goes through zero, so if you have zero voltage, nothing is happening. There's no electric field, so just the electrons are bouncing around randomly and not moving anywhere as a bulk thing. But as you put more current through the resistor, you get more of a voltage drop. And this relationship, where you have a linear relationship between voltage and current, that is called, it's a law. And so we have Ohm's law. And Ohm's law says that the resistance is equal to the voltage divided by the current. Or you could say that the voltage across the resistor is equal to the current times the resistance. Or you can say that the current is equal to the voltage divided by the resistance. Same equation, just written in solved with the three different variables. And if you have these are assuming they're constant. So you're having a circuit running and the current's constant, the voltage is constant, the resistance is always constant for the material. But you can also have it as a function of time. So if you had AC, you would have, I'm going to use this one, you'd say the voltage is a function of time is equal to the current as a function of time times the resistance. So it still applies even though it's varying. It's just the resistance doesn't change because that's dependent upon the material and the dimensions. But so if I were to run this experiment and I did it very slowly and I measured voltage versus current, I'd get this line. But even if I stuck a very rapidly oscillating voltage applied to a resistor, you would still get it exactly on that line. It's not affected by, the relationship is not affected by how quickly the voltage or current are changing with time. Okay, so what am I going to talk about next? So what if I wanted to calculate the resistance of an object? Because resistance is not a material property. Let's write that down. So R stands for resistance. First talk about units. So R is resistance, and the units are volts per amp. Volts per amp. But again, we give that a special name. We call that an ohm, and we use the omega to represent ohm. So the other day we used approximately 100 kilo ohm resistor, which is the same as 100,000 ohms. It's a pretty steep slope. Now, resistors are like capacitors. They don't come in an infinite number of sizes. So we have 220 ohm. There's a 470 ohm. I think there's a 1 kilo ohm. There's a 4.7 kilo ohm, 10 kilo ohm. So what we're going to do, we're not going to do it today, but probably Monday, we'll do the same thing. You can take resistors that are in parallel and series, and you can put them back. You can put them to reduce them down to an equivalent resistance. Okay, so those are the units. Ohms. Voltage is in volt. Potential, V is electric potential, which is in volts. Current is in amps. That's how we got volts per amp. That's an ohm. Okay, now, how do you figure out what the resistance? So I was going to say resistance is not a material property. Resistivity is a material property. And the relationship between resistance, which is a component property, so we can say it's a component property, right? Component property. A component's made out of a certain material, certain size. So, and we use the symbol rho, which is kind of confusing because that's also what we use for density. But usually, when you're dealing with density, you're not dealing with resistivity. So we use the same symbol. So it's a Greek symbol rho. And so the resistance is equal to rho times the length divided by the area. So let me define those. So that's rho. That's resistivity. And area, that's the cross-sectional area. In meters squared. L is the length in meters. R is the resistance in ohms. So what are the units for resistivity? So we've got ohms over here. We've got meters divided by meters squared, which means I've got meters in the denominator. So the units of this have to be such when I multiply this by meters, I get ohms. Or divide by meters, sorry. So if I take this unit and I divide by meters, then I should get ohms. So it is ohms meters. Because if I take, so let's just look at the units. If you take ohm meters times the length, which is a meter, divided by meters squared, you get ohms. Check. Okay, so I got that. That doesn't have a special name. Okay, it's just ohm meters. So the resistivity is usually a pretty small number when it comes to conductors have very low resistivities. Let's write that down. So conductors have very low resistivity. And let's look it up because I forgot my book again. So for example, the resistivity is generally given as 1.72 times 10 to the minus ohm meters. 1.72. So if you think about, let's think about what we did the other day. We had 100,000 ohms. So how much, and let's take copper wire that is a millimeter maybe in diameter. Let's see how long, to get 100,000 ohms made out of a conductor, how far would that have to be? So all we have to do is take the equation, resistance equals resistivity times length divided by area. So if you solve for length, you'll get resistivity times area divided by resistance area divided by resistivity. The area is pi r squared because it's circular. The radius is 0.001 divided by 2. So that's 1 millimeter squared. Cross-sectional areas are pretty small things. So let's see, we get pi times 0.0005 squared. So that's 7.85 times 10 to the minus 7 meters squared. Okay, so the length would be equal to the resistance, which is 100,000 ohms, times the area, which is 7.85 times 10 to the minus 7th meters squared, divided by the resistivity of copper, which is 1.72 times 10 to the minus 8th ohms. 100,000 times 7.85 e to the minus 7th divided by 1.72 e to the minus 8th, which is 4,600,000 meters, which is 4,600 kilometers, which is big, right? So yeah, it's pretty. It's you could have a long, very long piece of wire, which would have the same equivalent. Did I make a mistake? That seems awful big.
I was just going to ask where you got the 100,000 ohms from.
Oh, that was what we used the other day when we were doing our capacitor circuit. So it was just it's the capacitor that we, that little thing that we used the other day was 100,000 ohms. So since we use that, I thought that would be an interesting number to come up with. So even though the area is very small, the cross-sectional area is small, because the length or the resistance is so high and the resistivity is so low. I mean, what is that? That's like 2,000, almost partial of the way across the United States. So that shows you how much difference there is between a wire. That's why we can, even though you think, oh, we're going through wires, got to have some resistance, but relative to the resistors, it's essentially nothing. So that's why we don't even worry about the wires. Okay. So let's see, what time is it? 10:09. Okay. Well, let me see what I have on this thing here. Talk about that, talk about that. Yep. Yep, talked about that. Yeah, so here's the drift velocity. It's 1 times 10 to the minus 4 meters per second. The actual, if you look at the actual velocity of the electrons just bouncing around in a conductor, it's 1 times 10 to the 6th meters per second. It's pretty high. But the actual average movement because of the electric field is only 1 times 10 to the minus 4. It's a huge, huge difference there. Okay. So let's see what else I'm talking about.
It's sort of like sound, because the sound waves, you're looking at something that's moving really fast, but it's not necessarily moving across the room.
Right. Yeah. The molecules are still they're just moving here locally, but the sound wave can be moved way different. Okay. So that's what I'm going to talk about next. So since we're talking about this property, resistivity, is it a constant property? And the answer is no. Within a certain narrow temperature range, it is constant, or it's relatively constant. But the resistivity of the material is the resistivity at some reference temperature, which is usually 20 degrees C, which is room temperature. And then you multiply, if you want to find out the temperature other than the room temperature, T0, you take 1 plus alpha times the difference between the temperatures. So if the temperature is the same, then you just end up with the original temperature. So what this is, alpha is usually positive, so that if the temperature, the local temperature or the temperature of the wire is greater than 20 degrees C, then the resistance goes up. And if the temperature goes down, the resistance goes down. And that coefficient that relates the resistance to the temperature change is called the temperature coefficient of resistivity. So let's see, there's probably the next page tells us what the value is. So here's an example, just a ballpark answer. So where's my little screen thing? Oh well. So what is the resist? Well, we already looked at the resistive. Okay, so the number that I had earlier, the resistivity of copper was at 20 degrees C. So the question is, what is the resistivity at 100 degrees C? And as the resistivity increases, so does the resistance. So it turns out that alpha, this temperature coefficient of resistivity, is around 20 degrees C is 0.00393. The units are inverse degrees C, so it's 1 over degrees C. Here's the resistivity of copper, which we wrote down earlier. The reference temperature is 20 degrees C. So to find the resistivity at 100 degrees C, we take the resistivity at 20 degrees C, which is 1.72 times 10 to the minus 8 ohm meters. We take 1 plus alpha is 0.00393, times the temperature difference, 100 minus 20, which is 80, and it looks like it's 2.26 times 10 to the minus 8. So that's versus 1.72 times 10 to the minus 8 ohm meters at 20 degrees C. So it's not insignificant. What is that, about 5 units out of 17, so that's about 30%. It's about a 30% increase in resistance. So if you had to, if the value of the resistor was critical to your circuit working correctly, if it operated on 100 degrees C instead of 20 degrees C, and you designed it based on 20 degrees C, you could have 30% error in your whatever results. So it's not insignificant. Now the question might be, what happens if you keep lowering the temperature? Does the resistance of the material get lower and lower and lower? And the answer is yes. So I'm going to find a video here. So it's called superconductivity video. Let me see if I can hook up some. Let me, well, maybe I just need to, it's on there. Let's see, did I do it there? Maybe I'll just explain it. This is one example of a phenomenon associated with superconductivity. So what they have is, that's a magnet, and then this is a special kind of material. This disc is probably made out of solid something really cold. So basically you have this material, which is a superconduct material that has superconductivity behavior, and then you can take this magnet and basically cause levitation to occur. And that only happens because the resistance of the flow of electrons inside this really cold material is close to zero, or almost zero. Okay. And so these, magnetic levitation stuff. That's not really magnetic levitation. That's using some other thing. They have this, here it is, little train project. That looks good. Oh, there's video.
I write English all day, every day.
Maybe not. This, it looks like he's going to do some kind of magnetic levitation here, I think. Turn that thing off. I'm zooming ahead to see what the heck he's up to. Because if there's nothing involving cold, it's not really magnetic levitation. It's just, this is bogus. So, anyway, let's go back here. So anyway, if you do get to very, very low temperatures, the material becomes superconductive, which means, like I said, the resistance goes to zero. Okay, we'll spend the last few minutes going over these rules. We won't actually do a problem yet. We'll wait till next time. So you can take resistors in series and in parallel, and you can come up with similar relationships that we did for capacitance. But the relationship we use is not that capacitance is equal to charge over voltage, but we use the Ohm's law, which says resistance is voltage over current. So in this case, things are not happening instantaneously. You apply voltage and current flows, and you get to you basically you do almost immediately reach a equilibrium, but there's current flowing through the wire the whole time. The key thing about a series connection of two resistors is that the current through each resistor has to be the same. Because it's kind of like if you have a water pipe. The amount of water coming into the pipe has to be the same as the water going out the pipe. Otherwise, your pipe's got to get bigger and blow up. As long as pipe doesn't expand. So the same thing here is there's nowhere for the electrons to go, accumulate anywhere. So anything that goes through one has to go through the other because of the serial connection. So you do the same thing. Use Ohm's law for the first resistor. So you use the resistor 1 times the current, which is the same for both of them, is equal to the voltage across that. And then the voltage across the second resistor is the value of the second resistance times the same current. And the sum of the two voltages across the resistors has to be equal to whatever voltage you apply to the whole thing. So when you look at the equivalent single resistance, it has the same current, I, and it has the same total voltage across the resistor. So for the equivalent resistor to have the same current and the same total voltage drop, it has to satisfy this requirement. So V1, the voltage drop across the first resistor, plus V2, the voltage drop across the second resistor, has to be equal to the total voltage drop across the single resistor. So you just say the total voltage drop, which is the current multiplied by the equivalent resistance, is equal to the sum of the two voltage drops. And you'll notice that the I's cancel out. And when we did the capacitor equations, the charge dropped out, or the voltage dropped out, depending upon which configuration we had. So for a series connection of resistances, what happens is you just add the resistors together. Whereas when you had two capacitors in series, you had to use the reciprocal relationship. In the capacitor, when they were in parallel, you added the capacitors together. When you have resistance, you use the reciprocal relationship. So they're exactly opposite for the given parallel or series connections. So if you had a circuit that needed a 200 kilo ohm resistance, you would take two 100 kilo ohm resistors and connect them end to end. If you had two 100 kilo ohm resistors and you wanted 50 kilo ohms, you'd put them in parallel. So that's the equation. You just add the resistors together. And in parallel, what's happening is that the total current through these two resistors has to be the same as the sum of these two has to be the same as the current coming in from the left-hand side and the same current that's leaving the right-hand side. So when you replace these two parallel resistors with a single resistor, you've got this current, the sum of the two currents, has to be the same as the current that moves from here. So again, you use Ohm's law for these two, but instead of, you just say the voltage drop across these two is the same, and so you eliminate the voltage ultimately from the equation. Here we eliminated the current, and if you do that, you end up with this relationship. So for parallel resistors, the equivalent 1 over the equivalent resistance is equal to the sum of 1 over the individual resistances. And it comes down to the fact that just the arrangement of here the voltage is in the numerator, here the voltage is in the denominator, and that's why they get switched around. That's why one's one way and one is the other way. Okay, what else have I got here? Okay, so that's the example. I'm trying to not go to that yet because we'll work one in class. What I'll do is we'll give you the overview of how you do it, and then we'll do a specific one. So we have these two resistors are in parallel, and what you do is you combine these two into a single equivalent resistance using this formula. So we don't add them together. We'd have 1 over 3 plus 1 over 2 is equal to 1 over the equivalent resistance. And then once you reduce these two resistors in parallel into a single resistance, then what we have now is 3 resistors in series, and so you just add those 3 resistances together to get the final equivalent resistance. So if you can do capacitors, you can do resistors. So we're not going to do that yet. Okay, so I lied. I'll go one more thing. Come back to this. So there are two main, when you're analyzing a circuit. So this is where we're going to use the MATLAB thing in solving this next level problem. And the difference between this one and the one that I just kind of went through quickly, which will work an example in class on Monday, is that it has two batteries to it. And so it's got parallel and series resistors, but you can't combine all the resistors into one resistor with the way this configuration is. So we're going to figure out how to solve this problem. And to solve the problem, you have to use two of the biggest laws if you're an electrical engineer. So TJ is going to be doing this at some point because he's going to be an electrical engineer, or at least he wants to be. We'll see what happens. So so there's what's called they're called Kirchhoff's laws, and there's a current law and there's a voltage law. So the current law says that if you have currents that are flowing into a junction, so it's just four wires that are stuck together. What it says is that the sum of the currents into the junction have to equal 0. That's because the electrons that are moving in these circuits can't accumulate anywhere. So they have to, if they go in one place, they have to come out the other. So it's like if you have three people coming into, if you have, had a hallway and you have three people come into one part of the hallway, then the three people are going to come out the other end of the hallway at some point. Okay? Or if you had the hallway jam-packed, so I'm coming in and I'm going to get in there, you'd have to push three people out the other side. So what this drawing is showing, all three of these currents going in, so the current going out the fourth part has to equal the sum of the three going. So that's called Kirchhoff's current law. And the second one is called Kirchhoff's loop or voltage law. And we've kind of used that when we were talking about the capacitor resistor circuit. What that says is that the sum of the voltage changes around a loop is 0. Any loop. And again, you can think of it as elevation. If you start someplace and you walk around anywhere, but you come back to the same place, when you get back to the same place, you're at the same height. So the amount that you went down has to be the amount that you go up at some point. And you can use those two laws to solve complex electrical circuit stuff, to figure out, what is the voltage across each element, what is the current through each element. We're only going to be dealing with batteries and resistors. If you have capacitors, then it becomes time dependent, and it's, that's beyond the scope of this class. So one last comment. This has nothing to do with physics. So last night we had friends invite us over in our neighborhood, and one of the couples, everybody was retired except for me. And the other guy is, one of the other guys is a retired judge, so he judges sometimes, but he's mostly retired. And they're going to Australia and New Zealand next week. So they wanted to get together to talk about their last trip, which was to Italy and to Newfoundland and Canada. And so we're sitting around the table, and we're all neo-Nazi leftists, according to that description. We're all of the same political leaning, and it was like 11 o'clock, and I said, okay, I have to work tomorrow. You guys don't have to work. I got to go home. It's all very interesting. We talked about, it's amazing what we talked about. We could have talked for a long time, but yeah, because we're all. One thing this person talked about was she did ancestry DNA, which we talked about before, and she found a second cousin that lives in the United States, and they were getting to know each other and exchanging information about families. They basically have the same great-grandfather, and they actually live close to each other, but then they kind of lost touch when people moved. And then she said, and then I found out that she was a Trump supporter. And then I just said, I think I know enough about them now. So anyway, that was a funny comment. So they're still talking, but they didn't want to get to know them that much more. Apparently the whole family's ardent Trump supporter group. So it's sad that that happens, but yeah. Okay, that's it. That's my comment for the day. My political comment. Martha kept kicking me because she thought I was going to say something about my brother, which I wasn't. But